In this section, we have been introduced to the concept of a derivative, how the definition of the derivative was developed, and we also used that definition of a derivative to find the derivative of a number of functions. In this video, we're going to look at an alternative form of a derivative that we don't use very often, but there are specific cases where the alternative form of derivative is a little bit easier to use than the definition that we use most often. So let's look at how this alternative form of derivative came about. So again, we're going to look at a function like so, f of x. Now we want to find the equation of the tangent line at that point C. Alright, now we'll just again go back to the idea that we don't know how to find the equation of this tangent line, so what we're going to do is we're going to look at the equation of a secant line. So we have our secant line. And this point here we're actually going to call x. And so this is going to be the point x, comma, f of x. And this is the point C, comma, f of C. So let's go ahead and look at the slope of the secant line, which we know is going to be y2 minus y1 all over x2 minus x1. So then the slope of the secant line will be f of x minus f of c all over x minus c. Now in this case, c is a value. Okay. So this is going to be some number. So just like in the previous definition of a derivative, what we did was we said, okay, well we have this secant line, but that's an okay approximation for the tangent line, which is here. This would be the tangent line right here. But what if we took x and started getting it closer and closer and closer and closer to c? Well, as x became closer and closer to c, this tangent line would this secant line would slowly start becoming the tangent line. So what we'll do for this definition is we'll say that f prime of c equals the limit as x approaches c, so we're taking x and having it approach c, of f of x minus f of c all over x minus c. And so here is that alternative definition of a derivative. Alright, so let's look at an example of how this may be used. So for this example, if y equals x squared plus 3, we want to find dy dx evaluated at x equals 2. Okay, so here's some new notation. I did discuss previously that we've been using prime notation, but I did give you guys a list of other forms that say find the derivative, and this is another type of notation. This one's very unique because what this means, you have dy dx, that means find the derivative, then they put a line down, and then then you put here x equals 2. So this is telling us to find the derivative and evaluate it at x equals 2. And so we'll see this again, but I know this is the first time we've seen it. Alright, now because we're evaluating this at x equals 2, we can use this form of the derivative. So we're going to have f prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c. and in this case c is 2. So one thing about this alternative form of a derivative is you do have to have a value that you're looking for. So for this example, we are looking for the derivative at 2. So that means f prime of 2 is going to be the limit as x approaches 2. Now we need f of x, so that is x squared plus 3. And then we need f of c. Well, if c is 2, then we have 2 squared plus 3. And then this is all going to be over x minus 2. Okay, so to use this, you have your c, and then so here this has to be the c, which in this case is 2. This one just says take the function and evaluate it at c, which we did here. And now we need to evaluate this limit. And just like with the other definition of the derivative, this you can't substitute. You're going to get 0 right away in the denominator. So we're just going to have to simplify this, and probably the best way is first to just let's go ahead and distribute everything and combine like terms. So we're going to get the limit as x approaches 2 of x squared plus 3, take that to 4, so we get minus 4 minus 3 all over x minus 2. So then we have the limit as x approaches 2 of x squared minus 4 all over x minus 2, because these 3's cancel out. And then when you get to this point, depending on the problem, at this point of the problem, you have to somehow evaluate this limit. This one, quickly, I hope everybody saw that, oh hey, we can factor the numerator, so we should be able to cancel out a common factor. So we're going to end up with the limit as x approaches 2 of x plus 2 times x minus 2 all over x minus 2. The x minus 2's cancel out, and so we end up with the limit as x approaches 2 of x plus 2, which is, now we can do substitution, so that's 2 plus 2, which is 4. And so there is basically the slope of the tangent line at that point. So this is a nice little alternative form of the derivative. As I said before, we don't really use this particular form very much. And the reason is because if you notice, we had to evaluate this at 2. So if you were asked, well, now find the derivative with respect to x at x equals 3. Well, at that point, we would have to go through the whole process again. So the other form of the derivative is a lot better, because once you have the equation, then you can substitute in any value and get that slope of the tangent line. So let's write that down. So here's our disadvantage. You can only evaluate the slope one point at a time. Alright, so that's the big disadvantage. So some of you might be wondering, well, what is the advantage of this? There are a couple of advantages. One is with the other form of the derivative, if there does come a point when you're trying to find the derivative of the equation and that limit becomes really challenging, then maybe if you only need 1 point, maybe using this form might be a little bit easier. But the other advantage is for the following example. We're going to look at where a function might not be differentiable and showing that the function's not differentiable. And in those cases, this form tends to be a pretty good form to use. So let's take a look at that.